All right, everyone, we are going to get started with the next talk. I guess they're going to keep standing. The next talk will be from James Davies, who is going to talk about frame matroids with a distinguished frame element.
Thank you. So I've given plenty of talks by now, but this is a special talk for me because this is my first talk on matroid theory, which feels long overdue because I've been thinking about this for a while now. But anyway, it's been a really great workshop, and I can't think of a better place to give my first matroid talk. So thank you, everyone, for a great workshop. So I'm talking about frame matroids, and this is all joint work with Jim Geelin and Cynthia Rodriguez. So frame matroids. A matroid's a frame matroid if you can extend it by some basis, b, through these purple points, so that every element in the ground set of our matroid is within the span of at most two elements in our new frame basis. So, for example, here, this is a frame matroid because we could add in this purple basis, and every element lies in this line spanned by those two frame elements. So, one example of a subclass of frame matroids that everyone will have seen before is graphic matroids. So, this is just a graphic matroid of K4, and here I have a binary representation of it. So this is where I can give a frame, and it's a frame matroid. And for a frame in the binary representation, I can just add on the standard basis. And roughly speaking, what this looks like in the graphical representation is my frame elements are kind of like my vertices in my graph representation. So these edge elements lie in the span of these vertex frame elements. So frame matroids are more general than graphic matroids. They can't be represented quite so simply. But I mean, with this picture and this picture, it's really begging for some kind of graphical representation still. It's not just as simple as just having a graph, but you can still get some kind of graphical representation. And for this, we use bias graphs, which Dylan already talked about on Monday. So all that a bias graph is a graph with a set of balanced cycles. And we have one extra slightly technical property, that no theta subgraph, so theta being a free path between two vertices, no theta subgraph has exactly two balanced cycles. And this is just for matroidal reasons of when we go to define a matroid, we need this property for it to be a matroid. Okay, so we've got a collection of balanced cycles. So whenever we look at a cycle, it's either going to be balanced in a collection of balanced cycles or unbalanced. So this guy could be balanced, for instance, in which case I'll try and always make it green. Or if it's not balanced, then I'll try and always make it purple. Okay, so bias graphs, basically just graphs with a set of balanced cycles. Now you can define a matroid from this. The way you define it is your ground set is just going to be the edge set of our graph. And now the dependent sets are going to be the sets that either contain a balanced cycle or contain a connected subgraph with at least two cycles. So if all of our cycles were balanced, then this is exactly just recovering graphic matroids. It's just saying that the circuits are your cycles. But to get a feel of things, let's look at how the circuit can look like more generally. So again, if we're just looking at a balanced cycle, this is a circuit, and I'll try and make sure my circuits are always red. If it's unbalanced, then this is going to be an independent set. But now say, we could have another guy over here, another unbalanced guy. This is still independent, but now we add a path between them, and we're going to have a component with at least two cycles. And this is a circuit. And then this could be, we call this a handcuff, and this could be a more trivial path. So you can also have tight handcuffs of circuits. And we're not just restricted to like edges between two vertices. We can also have unbalanced loops. So together, this cycle and this loop, they're both unbalanced, and together they form a tight handcuff, a circuit. The other kind of circuit we can have comes from our thetas. So it could be that we have a theta where all three of our cycles are unbalanced. And in this case, we say the whole theta is unbalanced, and together this forms a circuit. It's a minimal set with at least two cycles. Okay. So from these definitions, it may not be so surprising that these are really the same things. These two definitions of frame matroids I've given you are exactly the same. Being able to extend with a frame basis is the same as having a bias graph representation of a frame matroid. So this is nice, we have these graphical representations of our frame matroids. Now, one nice thing about just graphic matroids, and this very classical result, is that actually we really for graphic matroids, we understand their graph representations perfectly. And in particular, if our graphic matroid's free connected, then we know our graph representation's unique. It's a very classical theorem. So unfortunately, this is not at all the case for frame matroids, and they can have all kinds of wild, inequivalent representations. So I want to show a few ways you can modify this balanced wheel and get different bias graphs representing the wheel. So one simple way is we can look at these top two vertices and kind of pinch them. So identifying these two vertices, making an unbalanced loop at the top, and then we've got these signed edges. So this is a signed graph representation now. Any cycle going through an odd number of these blue edges is an unbalanced cycle. And we can check that this is still defining the same matroid. So let's just look at a couple of circuits to get a feel of things. So in this representation, this guy is an unbalanced cycle, because we go through just two blue edges. So it's a circuit. And we can go backwards to our old representation, and it's just a different kind of balanced cycle. Another example is this handcuff is a circuit. It's made from two unbalanced cycles. And if we go backwards to our old representation, this is a balanced triangle, a circuit. So from here, you can go further and get more inequivalent representations. So you can do what's called a roll-up. So we can replace these two blue edges by just unbalanced loops. We're just rolling up these edges. And this, again, is a bias graph representing still the wheel. So, for example, we can have handcuffs like this, and if we went back, this is a circuit. If we went backwards, this was just a balanced cycle before. Okay. So this is not as nice, right, because we have a few different ways to represent already the wheel. But so far, I haven't shown you too many. It's not a complete disaster, right? But here's one quite nasty thing which shows that you can have really lots and lots of inequivalent representations. So to the wheel, you can do something called consecutive odd twisting, where basically we take an odd number of these segments going on the wheel and twist it into some kind of Mobius band. So now, again, I've got a signed graph where my signed edges are the ones going through the crosscap. And I can do this in an exponential number of ways because I'm just partitioning my wheel into an odd number of segments. So there's really tons of inequivalent representations now. So again, just to get a little bit of a feel, let's look at one circuit in this guy. We can look at this cycle that goes around the Mobius band twice because it goes through the crosscap twice. This is balanced. This is a circuit. And in our original representation, this is the same thing as the REM cycle. Okay. So one other nice thing about graphic matroids is actually you can recognize them efficiently just by doing a polynomial number of rank evaluations. So what would be great if you could do this for frame matroids, but this is not the case. Frame matroids cannot be recognized with a polynomial number of rank evaluations. We don't have there's no polynomial time algorithm for recognizing these guys. Let me rephrase this in terms of the original definition of frame matroids I gave. Given a matroid, we cannot determine in a polynomial number of rank evaluations whether it has a frame. So again, it having a frame is the same as it being a frame matroid. So now, the problem we looked at is, well, what if we're not looking for some arbitrary frame? What if there's some guy that we know we want to be in our frame, and we just want to test if this guy belongs to some frame? Then we can do this. So given a connected matroid and some special element of a matroid, we can test in polynomial time whether this matroid has a frame, which would make it a frame matroid, but with the additional property that a special element B is within our frame. So this we can do and recognize. And really this is a helpful tool if you want to do other recognition problems, right? Because if you can pin down something which in a frame, if you can pin down an element which you know in any possible frame has to be within that frame, then now you can just refer to this. So as soon as you pin something down, you can apply this algorithm. Okay. So the algorithm for proving this is quite basic and naive. I won't go into much detail, but it's one of these, like we do wheels and whirls, go down to a wheel or roll through contraction or deletions, and then we go back up, keeping track of our representations. So for a naive algorithm like this to work, you really need to understand your inequivalent representations well. And this is what our real theorem is.
I'm a bit confused with the last two theorems. Like if you use the last theorem and just run it over all b, all small b, then isn't it the algorithm to...
That's a good question. So your frame could be made entirely out of elements outside your matroid. So your frame, like we're extending the matroid by some basis, which is our frame. So it's just lying within some framed super matroid of it. Yep.
Sorry, can I ask a really dumb question? So when you say it cannot be determined in polytime, like, can you what does this mean, like, in terms of complexity?
I mean, this is just saying in terms of rank evaluations, you can't do it in polynomial time.
Okay.
This is somehow, if you're just given some underlying graph, the way they do it is that you can't distinguish whether it's actually representing or not because of these biases.
Okay, thanks.
Okay. So I should first say about an equivalent statement of this theorem. So as I kind of hinted to before, in a bias graph, the frame is kind of like the vertices. So if we're fixing some element B, and we want this to be a frame element, this is exactly the same thing as saying we want a bias graph representation in which our element B is an unbalanced loop. So this theorem of detecting if we have a bias graph representation in which our element B is an unbalanced loop is equivalent. So this is why we can just work with understanding these special types of inequivalent representations in which our element B is a fixed unbalanced loop. And something more we can do, if instead of just saying that our matroid is connected, we said free connected, then we can generate all such inequivalent representations. Okay. So to do this, the important thing is to understand the structure of these inequivalent representations. So our actual main theorem is a characterization of the inequivalent representations of a free connected frame matroid when we pick some element and just say this is always an unbalanced loop. So now, this isn't quite unique, but the representations aren't too crazy. There aren't too many. There aren't an exponential number or anything. it turns out they are equivalent up to what's called a twisted flip. So I'm not going to go through and define exactly what a twisted flip is, but I'll kind of show you some examples of this operation, and I'm not hiding too much. You'll have a pretty good idea of what they are from this. So a simple case of twisted flips I've already shown you, which is roll-ups. If everything is balanced, if I deleted this vertex, then I can do roll-ups, where I just look at one of these balancing class, like this blue guy, and roll up these edges into unbalanced loops. This is one simple case of twisted flips. There's also one more complicated kind of twisted flip you can do. So we can do this when we have this kind of structure. This green guy is going to be some balanced part of our bias graph. And we've got our vertex with our unbalanced cycle B up here. This can have some edges going into our balance component. And we're also going to have this kind of two separation in our graph with this component we call a blade. And now this blade can be unbalanced. Just inside this blade, we have a signed graph. So again, our unbalanced cycles are just the ones going through this blue edges once. And here's something you can do to get another inequivalent representation of this guy. We can detach these B and A edges, like so. And now we're just going to twist or flip them. So we're going to move the A up here, move B down there, and join them together. So all we've done is swapped this A and B. And I could have many of these things, and I need to do all of these at the same time in the same way. So for all of these, I'll be swapping the A and the B. Like so. Okay, so again, just to get a little bit of a feel and convince you this should be another representation of the same frame matroid, let's look at a couple of circuits. So we could have a handcuff like this. We've got an unbalanced cycle in both these blades, joined by a path. When we do this twisted flip, this is actually going to turn into a balanced cycle, so still a circuit. And it's balanced because we're going through these signed edges twice. One other example we can have, we could just have a circuit in here, this kind of handcuff. And now, when we do this twisted flip, we are changing it, but it actually looks kind of similar. So we're swapping this A and B, but this is still this kind of handcuff circuit. Okay, and this is more or less all you can do with twisted flips. So in equivalent representations, when we have B as a fixed unbalanced loop, they're all the same up to these twisted flips. And this is nice, right, and still applies more generally to not just when you're looking at something as an unbalanced loop. If you're looking at some kind of representation where you can isolate some unbalanced cycle somewhere, then perhaps you can do some contraction, get this guy down to an unbalanced cycle. From this theorem, you know the inequivalent representations, and then you can go backwards and possibly keep track of all your representations. Okay, so I want to talk a little bit about how you prove this, and really this is just like setting you off on the road on how to prove it. I'll get nowhere near, but this is kind of some standard technique on how you prove these theorems on inequivalent representations for frame matroids. So to do this, you really want to examine how co-circuits behave. So we can look at different types of co-circuits in our bias graph representation. So the nicest, simplest kind of co-circuit is vertex co-circuits. So these are just the co-circuits where we've got a vertex, and our co-circuit is just going to be the edges incident to this vertex. So this will be a co-circuit because we delete these edges, and then we're disconnecting our bias graph just by isolating this one vertex. We bump the rank down by 1. Now, if we had two different bias graph representations, and we know that some co-circuit is a vertex co-circuit in both, this is essentially like saying that the representation is the same locally around some vertex in both these representations. It tells us there's a vertex with exactly these edges incident to it. So if every vertex co-circuit was a vertex co-circuit, and every representation would have a unique representation. Unfortunately, as I've shown with these inequivalent representations, this isn't always true, so we need to examine what goes wrong. So the second kind of co-circuit we can examine is balancing co-circuits. So these are the co-circuits where our edges could be scattered throughout the bias graph, say, but when we remove it, we turn our unbalanced bias graph into a balanced graph. This bumps the rank down by 1 again. So this is something you normally have to fight with, but actually in our case of fixing an unbalanced loop, this is quite easy. We're only ever looking at when this guy B is an unbalanced loop. So if we're looking at some vertex co-circuit here, and we look at another representation where this guy's an unbalanced loop, this guy's never going to turn into a balancing co-circuit. So actually, we don't really have to worry about balancing co-circuits, which is nice. And then the other type of co-circuit is separating co-circuits. So it could be that in some other representation, this co-circuit turns into something like this. Where now if I delete these edges, I disconnect my bias graph into non-empty components where one becomes balanced. And this again can bump the rank down. So these are really the thing that you have to fight with. And because we have these inequivalent representations with twisted flips, these co-circuits can turn up. But then the nice thing is that really these are the only types of co-circuits. We only ever have vertex co-circuits, balancing co-circuits, and separating co-circuits. So this is really the starting point for going down the road of understanding inequivalent representations. So I said before that the separating co-circuits can turn up. So I just want to show where these appear in our twisted flips. Okay, so I've got this structure again, and I want to just look at the vertex co-circuit around this guy. This is my co-circuit. And I'm going to perform my twisted flip and see what happens to this co-circuit. I'm just flipping this guy up here. And now I see what happens when I delete this co-circuit. I end up disconnecting this component, and this guy also becomes balanced. So this is how separating co-circuits can appear. And you do need to deal with these, but you fight them enough, and eventually you're going to get to that. This is basically the only thing that can ever happen. You can still gain some information about edges incident to vertices and really examine what can change. And this ends up, these twisted flips ends up being really all that can happen if you fight long enough. Okay, I'll stop there.
Thank you, James. Does anyone have any questions?
So you're looking at frame matroids where a pair of unbalanced cycles are independent. Have you thought at all about, or do you know anything about lift graphic matroids where a pair of unbalanced disjoint cycles form a circuit?
So you mean this when we're fixing something as a loop, or?
Yeah.
Yeah, so these are actually easier because if you contract your unbalanced lift loop, then you're left with something graphic. So these end up being nice, and that lets you understand quasi-graphic if you fix a guy as well.
Are there any other questions?
Yeah, does your result, you might have said something about it and I might have missed it. Does your result generalise to I give you an independent set of the matroid and then you have a frame representation where that appears as an unbalanced cycle?
I've not thought about it, but my guess would be definitely not immediately. But maybe it's possible to do something like that.
All right, we are a bit short on time, so let's thank James again, and the next talk is in